Before I begin, two things. Today, 24 Victoria Crosses were awarded for the second relief of Lucknow in the Indian Mutiny. It's the most Victoria Crosses that were ever awarded in the United Kingdom. Secondly, I want to thank Crystal, all the rest of the guys that support us here in AV, Stefan, Alex, and some of the guys I don't know. They work in the background and they bring you this. So please give it up for them and give them a good round of applause for everything that they've been able to let me give to you, because without them I couldn't do it. I'm going to hazard a guess that what you think you're going to hear this morning isn't what you're going to hear. The other thing I want to point out to you that Craig, who's sitting down in the front here, isn't going to be talking about Edward III, who died in 1377. He's actually going to be talking about Edward VIII. There was just a number 5 missing there. All right, the miracle of water. I like to begin with something humorous. It seems appropriate. Think about it. Oh, we didn't get that. Okay, never mind. Water is one of the 4 ancient elements. It was believed that everything was made up out of water, air, earth, and fire. Water being one of the fundamental ones. It's shown here. And of course, they got it right. Water is cold and wet. And it was associated with various medical conditions. We know today that this is not true, but too much phlegm, for example, was the cause of a cold. And what you would do for that is do the opposite. So you would heat the person up. And sometimes the heating of the person was fairly drastic in certain circumstances. But that's in the old days, and we're not going to be talking about that. What is water? It's hydrogen and it's oxygen. I've shown it up on the screen here. 2 hydrogen atoms with 1 oxygen atom. They're not in a straight line, they're angled at a particular angle. And this gives water a unique property because it's a polar molecule. You see these pair of electrons here and here? Well, there's a charge there on that oxygen. And that's going to give us some very special properties that I will talk about as we go through this. And of course, you may have heard that water is a greenhouse gas. Yes, it is. It is twice as effective in trapping radiation as CO2. And why? Why isn't oxygen and nitrogen a greenhouse gas? There's molecules in there, they've got vibrational states. Carbon dioxide and water are shown over on the left. And the various transitions, the various vibrations are the things that absorb the energy that is being reflected from planet Earth. So here's incoming solar radiation. Oxygen and ozone take out the ultraviolet, CO2 takes out ultraviolet, water takes out ultraviolet, the total atmosphere takes out most of the ultraviolet, UVA gets down to us. But what we're concerned about is what's shown over on the right. This is the outgoing infrared radiation, and this is what's absorbed, and you'll see the CO2 there, some of it, and there's the total atmosphere absorbing CO2, and that bounces back down again. That's the problem, bounces back down again, so CO2 is one of these. Hydrogen has 3 isotopes. What do I mean by an isotope? It's the number of protons and neutrons that give us different isotopes. So hydrogen by itself is 1 single proton. Heavy hydrogen or deuterium is 1 proton and 1 neutron. And then tritium is 1 proton and 2 neutrons, and it's radioactive with a half-life of just over 12 years. So every 12 years it disappears. It is created naturally up in the upper atmosphere, but not a lot. We have D2O in normal water. It's about 1 molecule in 3,000 for HDO. That's a mixture then of the single proton and the single proton with the neutron. And then D2O itself, 41 million. 1 in 41 million. So quite rare, but you can separate it out. And in fact, that's what Canada used to do. it used to have heavy water separation plants to provide D2O to the CANDU reactors. We've got such a big stockpile now, we don't need to do it. Heavy water is more dense than water, and you can see over here, here's ice floating on water, and that ice at the bottom there is made of D2O, so it sinks. It's actually more dense. There's other issues with that. You can see the boiling point and melting point are slightly different. If you were to replace water with heavy water, for you, physiologically speaking, you'd get into trouble. If you replace normal water by 20% D2O, you'd run into problems, but you'd be okay. But if you increase that percentage by 5%, you become sterile. Maybe that's a good thing in some places. But if you get to 50%, you would die, because the reactions that take place in the body need to be able to break those bonds, and the D carbon bond is stronger than the H carbon bond. So processes start stopping to work in your body. That nice little picture underneath is ionized deuterium. Well, the origin, of course, of all this is back in the sky. The Big Bang made lots of hydrogen and helium, and through the stellar life cycle, all of the other elements are made. So oxygen is made in stars. So this is where that comes from. And the sun and planets, of course, are made from gas and dust clouds. They condense out through the gravitational influence. We end up with a disk shape that's shown over there, and it will start to condense. This is how the sun is made. This is how the planets are made. And in that gas, in addition to hydrogen and helium, there are other elements, there are other molecules, water being one of them. So water was present right from the beginning. This is the fusion cycle in the sun. This is only going from hydrogen to helium, but during that burning process, we are making heavier elements as well. So everything, with the exception of hydrogen, helium, a little bit of lithium, a little bit of beryllium, all made in stars. You're all stardust, as is everything on and in this ship. The amount of oxygen we estimate in the sun is enough to make 198 billion water Earths. That's a lot in the sun of oxygen. But of course, getting it out's another matter, but there's lots there. Where did that water come from? I've already alluded to it. Some of it was there in the beginning, right when the planet was made. Some of it was in the solar system, which formed the comets and meteorites and asteroids, and they impacted on our own planet, bringing additional water to the surface. The solar nebula was really the source of everything, because that's the whole system. But we know a lot of it has been present since we started to form. Over on the left, we're looking at the deuterium-hydrogen ratio in water. This is a fingerprint. So you see where Earth is. Earth is there, that's the ratio for Earth. These are some meteorites. This is Enceladus. These are some other bodies. There's Halley's Comet, and there's yet another comet. And you can see they differ statistically from Earth. So those are not the only source of the water on our planet. And then down below, you see what we estimate in some of the bigger planets. Again, different. So this is how we make our judgment. This is the same thing, but showing it in a slightly different way. JF, Jupiter family of comets. OC, Oort cloud family of comets. This is the big cloud that's on the outside of our solar system. And you can see that some of them agree with the deuterium-hydrogen ratio on our planet, and some of them definitely do not. So it's not all simple, and it's taken a while to figure it all out. Some of these some of these space telescopes have been looking at exoplanets, and we now believe that many may contain as much as 50% water. How do we know this? We can actually measure the density of the planet. We know roughly what the density of rock is. We know what the density of water is. You can combine these two to figure out what the effective density of a planet made of rock and water would be. And this is how you know how much water is there. It's quite straightforward, really. By weight, we've only got 0.02% water. Not very much at all. You've seen this before, I think, in previous presentations, both Kelly and mine. The big blue dot there is all the water on and above the earth. The little dot there is the liquid fresh water, and the tiny, tiny dot there is lakes and rivers. But there is more water within the planet. We estimate anywhere from 2 to 12 times the amount that's shown up there. All I'm showing you on the blue dots is what's on top that we can see and use. If you break it down, most of it's in the ocean. 96.5% of the water's in the ocean, and unless we do something with it, it's unusable because of the saline content. So the very small part up there, the 2.5%, the fresh water up there, we can break it down into groundwater and what's locked up in glaciers and ice caps. And then of that fresh other water, the surface water, we can break it down into what's in the atmosphere, the lakes, and what's in ice and snow. So you can see, really, despite the fact there's lots of stuff out there, we don't have that much. And indeed, many countries are going to become water stressed quite soon, if not already, as you'll see in the stress maps when I get to it. 90% of that surface water is here in Antarctica. Let's hope it stays there, because if it doesn't, sea level goes up by about 60 to 70 meters, if that was all to melt. Not a thing that we want to happen. Although the ice shelves here, there's the Ross Ice Shelf, and there's another ice shelf there, they are getting to be unstable, so we're a little bit worried about what's going on down south. Properties. I've listed properties of water up here and some different names for water. I mean, you're all familiar with water, but you can also call it oxidane, dihydrogen monoxide, and a couple of other names too. Interestingly, it's the only substance on our planet that exists in all three phases. This is the temperature versus pressure when it boils, and as you can see, as the pressure goes down from right to left, the temperature drops. And in the old days, this was one way to figure out how high you were. You would measure the boiling point of water, you'd know what the atmospheric pressure was, you'd know how high you were. So it was one way to figure out, if you were climbing a mountain, how high you'd gone up. As I said, it's the only substance that exists in all three phases: solid, liquid, and vapor. You might not be aware of the vapor because you don't see it, but there's lots of water vapor. You know that when you go out on a humid day, lots of water vapor in the air. So we've got all three phases, and this is unique about water. It's got a specific heat that's higher than most things. What does that mean, specific heat? It's the amount of energy you have to put into a substance to raise its temperature. This is a good thing, considering we're warming up the planet, because before the oceans are getting warmer and warmer, we have to put lots of energy in, although we are doing too much and the temperatures of the oceans are rising. We're getting some really hot pieces of ocean around the world now, which is not good. Tongue in cheek. This is dihydrogen monoxide. It is a very dangerous substance. Read the bullets. Pretty much anybody who's died has been exposed to dihydrogen monoxide. That's how fatal it is. Here's some more things. It's especially bad to give to dogs, because all vicious dogs have been exposed to dihydrogen monoxide before they attacked somebody. I said it was tongue-in-cheek. And you can look up more on the website. Acidity. Acidity is defined as the log of the hydrogen ion concentration. Well, that's actually a simplification, but for this purposes it's good enough. And water does ionize by itself. It ionizes into protons, it's a plus charge, H plus, into OH minus, it's a minus charge, and the neutral water, it does that at pH 7. There's a little bit of ionized material there, and pH 7 is what we term as neutral. If we go lower, it's acidic. Think of battery acid. And if we go higher, then it's caustic, and it becomes something like ammonia or lye. And this chart shows you the acidity of some common things. Remember the days of acid rain, some of you? We were concerned about the rising acidity in oceans and river water all over the place. Acid rain was definitely responsible for degrading some rock materials. We seem to have got that under control, but it is rising again. Acidity is rising in water, and this is how we measure it using the pH scale. This is how it's changed from the 1700s to the 1900s. So where you see it being more red, such as up here, then it's become more acidic in that period. Where you see it being white, it's either no data or it hasn't changed, but in general, it has gone up all over the world to various degrees. And the more it becomes acidic, the more dangerous it is for what's living in the oceans, which means it's more dangerous for us. Remember, 50% of the oxygen that is generated by the natural environment comes from the sea. If we mess up the sea too badly, we're in serious trouble. Rainbows. Water creates rainbows. And this is a lovely double rainbow that you can get sometimes. This is not my photograph, but this one is. And this is a double full half circle taken from the back of a ship as we left St. Petersburg. And water is responsible for that, splitting up the white light into the colors that you see in the rainbow. A lovely natural phenomenon. I don't have that in this talk, but there was a record rainbow in Taiwan that lasted about 12 hours. Yes, we are full of water, depending on our weight, our sex, and our age. You're anywhere from 60 to 70% of water. It's age dependent. There's more water in infants, and you see the figures up there. Total body water is what we refer to as the amount of water in you. This is why water, of course, is so essential for health and survival, and you'll see that in another slide as we get to it. So, some interesting facts about water. It dissolves more substances than any other liquid that we know of, so it's very good for getting something into solution. And if the water is pure, it doesn't conduct electricity, it's an insulator. So if you were to be in a bath of pure water and somebody pushed that electric fan in there, it wouldn't electrocute you. But it is the impurities in there that do that, allow the electric current to be conducted through water. So if you are suspicious of your spouse, make sure you bathe in pure water. There's some other facts. Water itself is actually colored. This is due to the vibrational states of the molecule. It is actually a pale blue. Yeah, you look out there and all of the blue you see is mostly reflected light coming from the sun. The other wavelengths are being absorbed by the water, and most of what you're seeing is reflected blue light. But it does have a color. The speed of sound in water changes depending whether it's fresh water or salt water. The figures are here. And sound goes much faster than it does in air, which is the bottom figure. It also changes with depth, as shown over on the right in the graph. So the deeper you go, the speed of sound changes. Something you may not know. This is the Mpemba effect. This is a very controversial observation. It works sometimes, but not always. And what is this effect? This effect is that a hot beaker of water will freeze faster than a cold beaker of water. You might have heard this, that hot liquids freeze faster than cold liquids. Not always. But the paper where it was actually published is shown here, Mpemba and Osborne in 1969 in Physics Education. And this is the graph from that paper. This is the initial temperature down here. So here we have 80 degrees freezing in 30 minutes, and here we have 20 degrees freezing in 100 minutes. This is not reliably reproducible, but it is reproducible under certain circumstances. This is something you might want to try with your kids at home. See if you can do it in the freezer. And that's to onset of freezing. It's not freezing solid, so you've got to be able to catch it for onset of freezing. We don't really know why that happens. There's a lot of theories about it, but we still don't actually understand why that's taking place. Right, this is the periodic table. I'm sure you're all familiar with this. It's not up to date because 118 here should be OG for Gamma-Son. I'll have to change that. But I really want to point out where hydrogen and oxygen are. They're both gases, and you can see they're non-metals in the periodic table. They combine together to give us this wonderful liquid of water. Now, if we look at group 4, group 5, group 6, and group 7 in the periodic table, and we look at some compounds that they make with hydrogen, in group 4 we start with methane, then we go to silane, germane, and stannane. They're gases. Plumbane is an unstable gas. It will decompose, but they're all gases. Group 5 go down from ammonia all the way down to bismuth. They're all gases, except for bismuth, which is an unstable liquid, so it decomposes. Jump over to group 7 and look at those hydrogen compounds from hydrofluoric acid all the way down to hydroiodic acid. They're all gases. And astatine is radioactive, so it's unstable. Now go to group 6, and we see that hydrogen sulfide is a gas, and hydrogen selenide is a gas, but water isn't. Now in the periodic table, if you remember your days from chemistry, there are trends in the rows, there are trends in the columns. But we don't have a trend here, do we? If we were following those trends, water should be a gas. But it is not. This is the main miracle, if you ask me, of water, that it's not a gas when it absolutely should be. And the proof is incontrovertible here. When you look at the comparison, it should be a gas. What's different? It's a rhetorical question. I don't expect you to answer that. The next slide does that. It's this. It's hydrogen bonding. Do you remember I pointed out when I gave you the structure of water that it was a polar molecule? You see the delta plus charges there, the delta minus charges on oxygen. So it is able to form linkages between other molecules due to this polar attraction. This is called hydrogen bonding. And as a result, we have a liquid. That's the reason water's a liquid. We don't have that feature in all of the others that I showed you on the previous table. There's no hydrogen bonding in them. Surface tension. Surface tension is an example of what's going on due to the polar attraction of the water molecules. It actually has what looks like a film on the surface that enables small things to float on it. And that's all due to the hydrogen bonding that's going on in water. The capillary action is also due to the same phenomenon. If you put water in a very narrow tube, it will climb up, as shown in this graphic here. You can see in the very thin tube, it's risen considerably above the very thick tube and the thinner tubes. Again, due to the surface tension, due to the hydrogen bonding, due to this feature that is unique to water. Density. You know that ice floats. And of course the people on the Titanic know that ice floats. The ones that survived anyway. It's about 0.92 versus 1. And very few substances, pure substances, do this. I've listed some elements here where the solids are less dense than the liquid versions of their elements. And I've given you the elements down at the bottom. One of them is arsenic, but this is quite a unique feature of water. If ice didn't float, it would all sink down to the bottom of the ocean and it would start to rise up and all the oceans would probably solidify. This is the density as a function of temperature. So here we have the density of water, and yes, the scale's quite expanded. There's 1, and the maximum density is at 4 degrees. It's not at 0. Again, another strange feature of water. Usually as you cool something, it gets more and more dense as it compacts. Not true with water. There's one form predominantly of ice on our planet. One form. But we have identified 19 different forms of ice. This is the way the molecules are arranged together in the solid. And of course, the way you arrange these gives that solid different properties. Most of the other forms of ice are actually more dense than water. They would sink, but they don't exist under standard temperature and pressure. So it's this packing arrangement that I'm referring to over here. This is what the phase diagram looks like for water. This is vapor down here. You can ignore that one. This is liquid. You can ignore that one. There's the triple point up there. Where's the triple point? There's the triple point there between a vapor, liquid, and ice. Here's the one that exists mostly at standard temperature and pressure. And all of those other forms, you'll see we either have to increase the pressure, which is on the left axis, or we have to change the temperature, which is on the x-axis. And it's in two different temperature scales. It's in centigrade at the bottom. It's in degrees Kelvin at the top. It's the same thing. Don't be confused about that. The message is clear. Increase the pressure, change the temperature, you'll get a different form of ice. But that doesn't exist under standard temperature and pressure. Sea ice. Sea ice freezes at about sea water freezes at about minus 1.8. And originally it's got brine trapped in it. So if you take fresh sea ice and melt it, you can't drink it. But as it ages, it actually expels the salt. And if you have old ice and melt it, you can drink it. And when sea ice melts, it doesn't really change the water level. It does change it a little bit because of the density differences between the ice and water, but sea ice is not an issue. What is an issue with sea ice is ice reflects radiation strongly, and if it disappears, the water absorbs radiation strongly. So you really change the energy budget in that area where the ice has disappeared. You've got more heat being absorbed by the oceans if you get rid of it. The water cycle, of course, summarized here. All of the water just keeps cycling around in this, and we keep recycling it, and that's important. Of course, in some areas of the earth, like the Atacama Desert, there is no water cycle because there is no water. It's probably the driest place on the planet. Snow. This gentleman here, Wilson Bentley, photographed lots and lots of snowflakes, about 5,000, and never found two that were alike. So we often hear that no snowflake is like another. Well, according to him, this is true too. And this is one of his examples, a couple are up there, and you can see his equipment for filming snowflakes. Ice can be very powerful sometimes. Over on the left, Niagara Falls stopped flowing in 1848. Over on the left and over on the right. Over on the right we have the Canadian Falls. Stopped flowing because everything froze up. Doesn't happen very often, but it certainly did then. This is an absolutely gorgeous photograph. I'm just showing a gorgeous photograph of ice. Ice can be very beautiful. For those of you who have traveled up into the north or the south and you've seen old ice from glaciers, you know it can be vividly blue. It's expelled all the oxygen, and what you're seeing then is the blue light being reflected from the sun, all the others being absorbed. Water on Earth, I alluded to this earlier, but this is the other theory that we've got lots of water from another body. This is Theia. Theia is a small planet that we think is the cause of the creation of our moon. There was a huge collision shortly after our planet was formed. This collision threw up material into space around the Earth, and it coalesced into what we have today in the moon. It could have been multiple collisions, but this is the most favored explanation for the creation of our moon. And Theia would have brought some water with it. and we have evidence for that. Drinking water. Drinking water is going to be a problem. This is a WHO report that lots of people are going to lack adequate supplies to drinking water. And indeed, just a couple of years, we're predicting that half the world's population is going to be stressed for drinking water. So aren't we lucky where we live? And of course, in my country, we've got a huge amount of fresh water that I'm sure you're all jealous of in the Great Lakes. Can't have it, sorry. This is stress now of countries that have problems. So the bright red is extremely stressed for water source. And do have a look at the way colors change. Over here in China, we've got orange. They're somewhere between 20 to 40% stress. And if we project out to 2040, it has gone higher. It's now red. It's now from 40 to 80% stress just in that one country. Other countries have changed too, so we're expecting water problems in the future. It's a resource that we have to really look after and be able to deal with. Anybody know where that picture comes from? I heard something, yeah. Well done, Marathon Man, it is indeed. Put dentistry back 10 years. Is it safe? Is drinking water safe? 1854, there was a cholera outbreak in London. This source of the water was the water pump. It was identified by Dr. John Snow, and the way he solved it was to remove the pump handle. He saved a lot of lives. This was probably the first public health act and was the beginning of the science of epidemiology in England, in London, because of that cholera outbreak. 1988, there's another example of water being poisoned in Camelford. 20 tons of aluminium sulfate got put into the wrong tank and it got into the water source. Another example in 1993, that was fluoride poisoning that got into the water source. There's many examples of this. This is one from my own country in Ontario. This is Walkerton, where E. coli got into the water. Material from a farm got into the aquifer, and the E. coli got into the aquifer, and as a result, 7 people died from that, and hundreds more suffered from symptoms before it was actually tracked down, and they figured out what it was. It was a huge, huge scandal in Canada. We found plastic in drinking water. Well, plastic seems to be everywhere, and we found it there. Typically more than the size of a human hair found in plastic. 10 pieces. You can drink too much, believe it or not, and it can actually kill you. This particular article, which came out in 2007, was about a woman who lost her eyesight through drinking too much water. When you drink water, you should also balance the electrolytes that you put in. If you just drink water by itself, it's no good. And it can indeed lead to death if you dilute your own electrolytes too much. There's a special name for it, hyponatremia, if you're drinking too much water. If you get thirsty, it's telling you, your body is telling you that you're low on water. You've lost anywhere from 1 to 2% of your body weight from water. That's why you're thirsty. So these are some recommendations of how much water you should be taking in during the day. It doesn't have to be a tumbler of water. It can be in foodstuffs. It's just how much water gets into your body. And those are the recommended limits. Of course, in hot climates, you're going to sweat more. You need to drink more. If you're in the desert, you probably should be drinking every 20, 30 minutes, putting in a cup of water. It just depends what you're doing. Of course, if you're working hard, again, you're sweating and you need to drink. CDC has found a number of incidents, of course, of GI illness coming from water sources. These are some results of 1,000 bottles that were tested of 103 brands, and you can see the results there. A bit alarming, really. There's high percentages that exceeded limits, either in states or health warnings, and 8 cases had arsenic in them that were above approved levels. This is summarizing why we drink what we drink. Bottled water. Most successful advertising campaign on the planet, in my opinion. Worried about tap water safety, 35%. Worried about tap water safety and substitute for other beverages, 12%. Substitute for other beverages, 35%. Taste, yeah, I'll get to taste in a minute, and other reasons. That's why they drink bottled water. A few examples of a couple of well-known brands. Perrier was studied. Pass on Perrier. I'm not going to read these bullets. You scan that. San Pele is the next one. It's also a pass. Actually was a favorite of mine until we started making this stuff at home. We now make it at home with a Soda Stream. And that's a pass too, although they did find a few things in San Pele. Bottled waters. Look at the market. By 2030, we're projecting 500.7 billion in sales. That's why I say it's the most successful advertising campaign ever. They're selling it. There's nothing wrong with your tap water in North America. Why are you drinking bottled water? Unless, of course, you're living next to a fracking site, and then you probably do want to drink bottled water. This is the taste test.
What was the actual source of these chic waters? A garden hose on the restaurant patio.
My name is Tim, and I will be your water steward tonight.
Cool.
Little du robinet?
Yeah.
Oh, fantastic.
Okay.
It's French for tap water.
And for you, sir, would you like to try one, maybe compare notes?
Yeah, do the other one.
Sure, I'll do the Mount Fuji.
The Mount Fuji?
Yeah.
It has a flavor to it.
How would you compare it to tap water?
Oh yeah, definitely better than tap water. It doesn't have an aftertaste to it. It's got a flavor that it almost feels like a beverage other than water, but without sugar or any additives.
It's right from the top of Mount Fuji. It's a very pure water. It's a natural diuretic and an antitoxin.
It does feel glacier, like it does.
Glacier oriented.
Yeah, this is good.
Yeah.
I've taken the liberty of bringing you a bottle of our Agua de Culo.
Okay.
It's $6.50 per bottle.
It's got a very fresh taste to it. It's crisper. It has a crisp.
More of a kick. I like that.
Surely this couple wasn't representative. Let's see how some other people rated our premium hose water.
It's smoother than tap water. Better than LA County water.
We're pretty sure the hose added that glacial taste that was so widely praised.
Speaks for itself, right? These are countries in red where you would want to be drinking bottled water. The countries in blue, the water supply is safe, unless, of course, something has happened, an unusual event. But that breaks down the world for you, where things are safe and where things aren't safe. Seawater, I've mentioned already that we've got all that water out there that's unusable for us as it is. There's too much salt in it. You cannot drink it. It is too high. There's 3.5% of salt in water, weight for weight, or volume for volume. And the maximum you can tolerate in water is about 0.9% of salt. Anything other than that, if you drink it for an extended period of time, you're going to go mad and dead. So you get stuck on that desert island with no water source and all this water around you. What a tortuous way to go. You can't do it. But the Baltic Sea is a different place. What this map is showing you is the salt content of the Baltic Sea. And in some parts, you can see it's getting low in parts per thousand. Around about the middle there is what you can tolerate, where my mouse pointer is. So where you see that, you can perhaps drink some of the Baltic Sea directly. There's a lot of fresh water that flows into the Baltic Sea, and it doesn't exchange very well with the Atlantic Ocean. So the salinity is over to the east. It's about the only place on the planet you can do that as far as it goes. Hot weather, dehydration in hours. This is an article that came out in 2017. You don't leave children in hot cars. You don't leave dogs in hot cars. They'll die. They'll dehydrate quickly. Water's very important. How about you? You want to commit suicide? Stop drinking water for up to 5 days. It'll take about that length of time. If you're working hard, quicker. But basically, you can't go for more than 3 to 5 days without water. It'll kill you. Time, we have used water to tell time as far back as 4000 BC in China. Over on the right here, we see an unusual water clock that's showing the time of 4:06. And over on the left, we're showing an example of a water clock where water would come out of a hole underneath. Down here, down the hole, there's a hole down there, and as the water level went down, you could tell time. Water clocks have been around for a very long time. Of course, you need to correct them. They will vary on temperature and humidity. They will alter them, so they're not that accurate. So corrections sometimes have to be made. You probably have to reset it every day from a sundial. Those are the viscosities, and for every degree change, of course, as I mentioned, things go wrong with water clocks. But that's something you could also try at home with your kids if you wanted to. Put a little hole in a big pop bottle, calibrate it, and make yourself a clock, and do that. And that brings me to the end of the miracle of water. We have Science Cafe today in Engage. I'm told refreshments will be served, unlike when we were in the club. And that's where we reverse science trivia. I'm not asking you questions, you're asking me questions. So if you've got any burning science questions from anything on any of the talks you've seen, or anything to do with science in general, or even dog behavior questions, we'll both be there at 1:15 in Engage. Thank you very much.